All right, up to this point, we have talked about gravity in terms of using it when looking at projectiles or objects falling, or even to calculate weight, but we really haven't explored the idea of what gravity actually is. So, we're going to take a look at some of the key historical developments for our gravitational theory, and one of the most famous quotes of all of science is Isaac Newton. It says, "If I have seen so far, it is because I have stood on the shoulders of giants." So, the goals for this lecture are to understand the scientific theories are constantly refined as experimental evidence changes. Okay, this is a real pet peeve of a lot of scientists because somebody will say, "Oh, well, of course it was wrong. It was just a theory." Okay, a theory is the best explanation at the time and can be modified as new evidence presents itself. And you'll see that as you kind of work through some of the key aspects of gravity. And number two, you should understand the key points in the development of gravitational theory, including people and experiments that led us to believe what our current gravitational theory is. So number one is Aristotle. He was a Greek philosopher, and he was the first of the empirical scientists. So what that means is he was the first person to actually distinguish and use experimental evidence to distinguish between what actually happens from philosophical arguments. So up through this point, it was considered to be the highest possible argument to use logic to deduce scientific principle. In other words, you say, "Oh, well, it must be true because of this." But Aristotle was the first one to start to use empirical evidence, in other words, experiments. Now, he didn't place it above logic, but he thought that it paired with logic fairly well, although he still thought logic was higher on the totem pole. So Aristotle believed that everything sought its natural place. In other words, a rock has a natural place on the ground. In order to remove the rock from its natural place, you had to do violent motion. And then what happened would be everything would naturally seek its own place. So this is the first kind of explanation as to why things fall or things move to the side, why a river flows, and things like that. That was the predominant view for a large amount of time, but Aristotle's very important because he's the first of the empirical scientists. Okay. A long period of time passed, and there are some scientists that made some significant contributions, but the next major one would be Galileo. And Galileo was an Italian scientist. He discovered the moons of Jupiter, but in terms of relationships to gravitation, what he did is he did several experiments with a ball and a ramp. And what he did is he took various ramps of different inclines, and he would roll the ball down one incline and see how far it went up on the next incline, and then he would roll it from this one and see how far it went up on the next one. And what he discovered was that acceleration is actually independent of mass. So you could take a really heavy ball and start it here and roll up to this point right here. You take a really light ball and you could roll it from here and it would roll up to about the same point, presuming that these ramps right here were very, very, very smooth. And what we know now is if these ramps are very smooth, what they're doing is they're reducing the amount of friction that's present. Galileo was also famous for supposedly dropping off two different sized cannonballs off the Leaning Tower of Pisa. Now, there's some historical debate of whether or not this actually occurred, or whether he just said he could. But the basic idea was that Galileo discovered that acceleration itself was independent of mass. Now, Galileo and Newton are very much related. They were very similar in a time frame. Newton came almost immediately after Galileo's death. This class is primarily called Newtonian physics. We've talked about Newton's laws of motion already. And we said that he made great leaps forward in motion and light and calculus. But the thing that sets Newton apart from anyone else is his law of gravity. Okay, his laws of motion are great. The fact that he invented calculus, well, somebody else did that at the same time. Other people have done a little bit better work with light. But the law of gravity, uniting what happens in the heavens and on the earth, is what made him truly one of the giants of science. So what Newton said, supposedly it started with an apple. That an apple fell on his head, or he saw an apple fall and said, "Hey, I wonder if the moon is falling towards Earth." And it was that logical insight, that leap that led him to look at, okay, well, what if the moon is falling towards the Earth? And work out a proportionality. So he was able to deduce that the moon is falling towards the Earth. Now, the reason why the moon doesn't hit the Earth is that the Earth actually moves. The reason why the apple falls and hits the Earth is, well, the Earth doesn't move that much. So it was one of those things that united saying, hey, the moon is just like an apple. That was a big, big leap forward. So What he found was that this deduction, this belief that the moon is falling, was consistent with all of his other laws of motion. The principle of inertia, the principle of F equals ma. It was consistent with Galileo's acceleration experiments. So this idea that the moon falls and that an apple falls and it's all related to gravity has been proved multiple times with experimental verification. However, Newton's gravitational law was a proportionality. What that means is, as mass goes up, gravitational force goes up. As distance goes down, gravitational force goes up. But it wasn't an equality. You couldn't say, hey, if mass doubles, then this happens. It just said that they were related to one another. What it was missing is a constant value to set it up and turn it into an equality. And that was actually experimentally determined by Cavendish in this experiment. What he did is he had two heavy balls right here, and he had this massive apparatus that was right here. And what he was trying to do is he was trying to measure the gravitational force that was existing between these two cannonballs. Now, as you know, the gravitational force is very, very, very weak. So this experimental setup required a lot of finesse in order to set up. But Cavendish, because of his experimental finesse, was able to determine that there is, in fact, a gravitational constant that can take Newton's proportionality and turn it into an equality. Now, there are some flaws with what's called Newton's law of universal gravitation, or N-law. Okay? It fails at very, very large mass values. And by very large mass values, I'm talking about things that are the size of or the mass of a black hole. So things that are much, much more massive than Earth and so forth. Very, very heavy stars it also fails at. And by fails, I don't mean that it completely breaks down, but the predictions of Newton's law of universal gravity doesn't quite match what is actually observed in the experiment. Also, Newton's law of universal gravitation doesn't work for high-speed objects such as light. So light was generally considered to be massless, but at the same time you could see that light was bent. So there's a flaw in it somewhere along those lines as well. And the biggest flaw of Newton's law of universal gravitation is it doesn't actually explain why there's any gravity. It kind of says, okay, well, this is what gravity, we can predict how gravity will act, but it doesn't explain why gravity is there to begin with. So there have been generally no improvements to Newton's law of universal gravitation since Cavendish. So it took another genius, Einstein, to actually correct Newtonian gravity with what he called his theory of general relativity. And what he suggested was that gravity is the curvature of space-time due to mass. So in other words, the Earth, this is a three-dimensional representation of what would really be four-dimensional. But what you see is the Earth creates a kind of warp or a curve in space-time. And the satellite actually kind of travels along this. Like, have you ever seen where you take a coin and you put it in one of those little funnels and it goes around and around? Well, that's the same basic idea that the satellite is going around. But since there's no friction, the satellite doesn't slowly work its way down to the center. So that's the Einsteinian view of gravity. There was multiple experimental verifications for that as well, including an expedition to measure how much light is bent during a solar eclipse. And that's what we're talking about here. You can see that the light is actually bent around whenever there's an eclipse, whenever the moon goes in front of the sun. And it was confirmed in 1919 by Sir Arthur Eddington. And so as a result, that was the experimental verification that, hey, Einstein's correction for general relativity actually works. So what he did is he took Newton's law of universal gravitation that is correct 90% of the time, and he said, okay, well, I can make it true the rest of the time. The problem is it still doesn't work 100% of the time. You may have heard the news lately that they've been looking for something called the Higgs boson. We took it and now we know 99% of the time gravity works. But what happens is when you start to look at things very, very, very small, relativity breaks down and it doesn't work. So what we're trying to do is we're trying to find a quantum theory of gravity. And that's actually the last thing that's missing from a so-called theory of everything. And so they're looking at things like gravitons and Higgs bosons. And so what they do is they've been looking at the CERN super collider, and they've been colliding particles together at very high speeds to try and find remnants of this Higgs boson. And if they can do that, they can actually show and say, we have a quantum theory of gravity. So we'll have a theory of gravity that will work for things very small, and things that are very, very large. And that's the last thing that we have to do in terms of a theory of gravity. Now, you should understand that scientific theories are constantly refined as experimental evidence changes. So, Aristotle had his idea. Well, then there was experiments done by Galileo that kind of changed what that was going to be. And then Newton came up with his idea. And then Cavendish's experiment modified that theory. And then Einstein had his theory. And then Eddington's observations confirmed it. But then we have these multiple, it's a constant ebb and flow between experimental evidence, theory, experimental evidence, new theory. And it's a continual process that you'll see in just about any scientific theory. It's very important that you understand these key points. You need to know Aristotle, Galileo, Newton, Cavendish, Einstein, and their significant contributions to this gravitational theory. There is no quiz for this particular lecture because it's all just stuff that you have to memorize or commit to memory. So there's nothing to work out, but you do need to go over this and take good notes over this lecture.